if you think about waves just a little bit, you'll know that waves have to carry some amount of energy. So say I have a speaker over here, and let's say I'm playing very, very loud music. Very, very loud music, strong bass. That strong bass, if it's loud enough, will actually start to vibrate the walls in the building. If you've ever been next to somebody in a dorm room, or somebody across the hall from you is playing loud music, you know the walls can actually start to vibrate a little bit because of that music. The walls themselves start to shake. So it's clear that there's got to be some energy being transferred in the form of a sound wave from the speaker to the walls. So we want to characterize that. We want to quantify how much energy is being spent. So we're going to look at the power being emitted by the speaker, or whatever source of wave this happens to be. And just a reminder, power is the change in the energy divided by the change in the time. So how much energy is coming out of the speaker every second. And it turns out power itself is not necessarily the most useful measure. Why is power not the best measure for the amount of energy that we are absorbing when we hear a sound wave? Well, let's say I have a speaker. My speaker is emitting waves in all different directions. There's this giant circular sound wave that's coming out, and that sound wave is traveling out further and further every second until it hits my ears. Well, originally, all of my energy was in a very, very tight spherical shell right around the speaker. Now we have the same energy, but it's spread out over a much larger area, a much larger sphere. So the amount of energy that we have in a given unit of area, let's say I take some area that's that big. Well, this is a small percentage of the big sphere, but the same size area is comparatively a larger percentage of the smaller sphere. So we're losing the density of energy. Our energy is getting less and less dense. This is why it's difficult to hear sounds that are very, very far away, because the energy stored in that sound gets weaker and weaker, or the energy density gets weaker and weaker the further away you get from the source of the sound. So if we want to monitor the energy coming out, we really don't just want the total energy coming out. We want to find the energy coming out, or the power coming out, per unit area. We call this the intensity of the sound, or the intensity of the wave, because light has an intensity as well. This works for more than just sound waves. So the intensity is the power per unit area. Now, if it's a spherical wave where the sound is coming out in all directions, my energy, my power, is being spread over the area of a sphere, which means I want my power P divided by the area of a sphere, which in this case is 4 pi times the radius of that sphere squared. So as the radius gets bigger, we have a less and less intense sound. Let's just box this off. We'll see this quite a bit throughout the rest of our discussion on waves. Suppose I double the amount of energy stored in a sound wave. Well, my ears perceive that as being twice as loud. Well, it turns out human ears are very delicate. So we don't want a huge amount of energy going in and rupturing our eardrum. So for that reason, we've evolved mechanisms that reduce the amount of sound entering our ear if it gets too loud. So it turns out we don't actually hear things on a regular old linear intensity scale. We hear things on more of a logarithmic scale, where the energy, if we double the energy, it doesn't get twice as loud. The way to see this is through the decibel scale, or the way to measure this is through the decibel scale. So you may have seen audio equipment where the volume of the sound is measured in decibels. Decibel is just a different type of unit, but it's a little bit screwy. So most audio equipment that you buy has some decibel level. Maybe they go up to 10. Turns out in the physics department, ours goes up to 11. Some of you will get that reference, most of you won't. Anyway, bad jokes. Decibels are defined this way. They're a little bit screwy. If I want to know the decibel level of the sound given by the Greek letter beta, we're going to define this to be, you'll get 10 decibels of sound. Given a certain intensity. But to get that intensity, to convert that to decibels, to convert that intensity to decibels, you want to take the logarithm of the intensity divided by I naught, which is a reference intensity. The I naught, the reference intensity, is 10 to the minus 12 watts per meter squared. That's about the lowest volume sound that our human ears can hear. 10 to the minus 12 watts per meter squared. I plug that reference intensity in here. I plug the actual intensity of the sound wave in here, and I calculate what my answer is. That tells me how big the sound is in decibels. So to give you a rough idea of how the decibel scale works, it's helpful to consider some examples. So we're going to go from 0 to 188 decibels. What do these sound levels, sound intensities correspond to? 0 decibels. We can barely hear that. The softest thing you can hear, that's 0 decibels. 20 decibels. That's about the volume of a whispering. So if I'm whispering to you like this, that's about 20 decibels. 60 to 70 decibels, that's about normal speech. The way I'm speaking right now, that's about 60 to 70 decibels. 120 to 130 decibels. That's starting to get painful. Something that's 120 to 130 decibels starts to be so loud that it hurts your ears. What if we go beyond that, 150 decibels? Well, that's your standard rock concert. Might want to wear ear protection for that. 188 decibels. Well, very few things can make sounds of 188 decibels. But blue whales, it turns out, are one of those things. So the songs that blue whales sing are at about 188 decibels. Now you might ask, what is the loudest sound that has ever been recorded? If my research is still accurate, by the time this gets posted, the loudest sound ever recorded was 246 decibels. It's still not entirely clear what caused it, but it seems to be emanating from deep in the ocean. And it has been given the name the bloop, because if you play an audio sample of it, it goes, it sounds a little bloopy. But that's at 246 decibels. Very, very loud sound. Again, this is a logarithmic scale, so what we're doing is every time these go up by 1, really the intensity level is increasing by a factor of 10. Why does the sound's pitch change if its source is moving? That has to deal with something called the Doppler shift, or equivalently called the Doppler effect. So let's say I have a car that's emitting some sound. I'm going to call the sound my source. The car is my source. And over here, here's you. You are the observer. You observe that sound. You are known as the observer. Now, to start off with, let's say the velocity of the source and the velocity of the observer are both 0. So nobody's moving. But the car does have a loudspeaker on it, and that loudspeaker is playing. And it's emitting sound, and that sound has a certain wavelength. So that's the distance between the two peaks in the wave, which I'm representing here with those little slightly curved lines. So it has a certain wavelength, and therefore it has a certain frequency. Now, how frequently are you going to hear that sound? Well, if you're completely still, and the source of the sound is completely still, then what's going to happen is you're going to hear them just as frequently as they came out of the car, or just as frequently as the speaker was making those sounds. So in this case, if the source and the observer are both stationary, you should hear no shift in the frequency of the sound. Let's say both my observer and my source are stationary. Well, again, the source emits some sound. The sound wave travels a certain distance. It then emits another pulse of sound or another peak in the sound wave. The spacing between those two peaks is the wavelength. Now, let's change that up a little bit. Let's say my car is actually moving forward with some velocity, which I'll call Vs, for the velocity of the source. Well, if my car is moving to the right, it's going to have traveled in time t some distance which is equal to the velocity times the time. So now my car is going to have moved forward a little bit. My sound wave is also going to have traveled forward. It's going to have traveled forward this distance, so that the pulse that was emitted originally is now going to be over here by the time that the car has moved forward. So let's see where my car is relative to the first pulse of the sine wave, of the sound wave, excuse me. All right, well now, pulse is still in the same spot, but the car has moved forward, so that by the time it releases the second pulse of sound, it's now been trying to catch up to the first sound that it emitted, which means there is a new spacing between those two sound waves, which means I am going to have a new wavelength. A new wavelength which is smaller than my original wavelength. So we can write that my new wavelength is smaller than, less than, my original wavelength. Equivalently, since wavelength and frequency are inversely proportional, that must mean that I have a new frequency, which is greater than, because they're inversely proportional. Gotta flip the greater than, less than sign. My new frequency is greater than my old frequency. Since my sound pulses are spaced closer together, I am going to hear them more frequently than I would if the car were not moving. Let's say you are moving towards the source of the sound. Well, the car is still completely stationary. It's emitting sound with the same wavelength that it did before. And if you're moving towards it, you're going to experience those peaks and waves even faster. So you might hit the first one, the first peak in the sound wave might hit you when you're here. But by the time the second peak hits you, you're going to be a little bit closer. So you are going to hear that increase in the pressure of the sound wave even faster. So the peaks of the sound wave are arriving to you more frequently. Therefore, the frequency of the sound will increase. So in this case, if you are moving towards the object, we would expect that the frequency of the sound will increase. Let's see if we can express the Doppler shift mathematically. We have three speeds we're concerned with, one of which is the speed of sound, one of which is the observer's speed, one of which is the speed of the source. We can express mathematically the change in the frequency, so my new frequency, compared to my original frequency, f naught, using this equation. Let's see how this works. I've got the velocity of sound, plus or minus the velocity of the observer. So, the plus or minus I am going to determine based on whether the observer is moving toward the source of the sound or away from it. If my observer is moving towards the sound, I expect my observer to hear the sound, the peaks in the sound more frequently. Therefore, if he's moving towards the sound, we'd expect he would get a plus sign here. Because the frequency, we want a larger frequency, he's going to hear the sounds more frequently. We want a plus sign there to give us a bigger frequency, bigger number for the frequency. If he is moving away from the source of the sound, I expect that I'm going to hear the sound less frequently. Because I'm running away from the sound, it's going to reach me not as often as it would if I were moving towards it or standing still. So if you're moving away, you want to have the negative sign in here, so that you are not hearing the sound as frequently. What about the velocity of the source? Well, if the source is coming towards you, again, the two objects are coming together, source and the observer, you expect to hear the sound more frequently. If that's the case, I want to use the minus sign in here. Why minus if the frequency is getting bigger? Well, we're in the denominator, so we want to divide by a small number to get a bigger frequency. So if the source is moving towards the observer, we want to use the minus sign. If it's moving away from the observer, we expect that frequency to go down, so we want to use the plus sign. This can get a little bit tricky, but you just want to think about physically what's going on. Do I expect to hear a larger frequency or a smaller frequency? Is the pitch going to go up or is it going to go down? That tells you whether or not you want a plus or a minus in both the numerator and the denominator. Here's an experiment I rather enjoy that shows what happens when you combine two sound waves together. So I have two function generators. They're both pumping in sine waves into the same audio speaker. We're going to see what happens when the frequency of those two sine waves is just slightly different. Here we are. Let's start with two function generators operating both at 100 Hertz. So they're at the same frequency now. That's one. That's two. I'm going to change the frequency of the bottom function generator, and I think you'll agree something interesting starts to happen. Let's try changing that frequency a little more. When we play two sounds that are close in frequency, you clearly hear beats. Now you may also have noticed that when the frequencies were closer together, the frequency of the beats was lower. And as the frequencies of the pitches got further and further apart, the frequency of the beats increased. Well, there's a reason for that. If I look at the beat frequency, so how often do I hear a beat? So maybe you hear a beat once a second. Maybe you heard a beat twice a second. When you hear beats, the beats come in at a certain frequency. I'm going to call that frequency F. The only thing that F depends on is the difference between those two frequencies. In fact, the beat frequency is exactly equal to the difference between the frequency of sound 1 and the frequency of sound 2. Why is that exactly? Well, let's take a look at Mathematica and plot two different sine waves with close frequencies and see if we can determine why there's beats. We're going to plot our sound wave using Mathematica. So here we see just a simple program that plots the superposition of two sound waves, two sine waves specifically. We can see here, let me just highlight what we're plotting. We have two sine waves here. It's the sine of a 196 hertz wave plus a sine wave that has a frequency of 197 hertz. And when we plot that, we get the graph below. I can run that again. Let me just do that quick. Refresh there. And we see we get the plot below. It's got several peaks. Nothing too surprising about that. But our peaks don't exactly match up. So we're going to see what happens when I also plot the two individual sine waves, the two sound waves, at 196 hertz and 197 hertz. Let's just run that. Okay. We can see that the two waves, the red and the blue wave that you can see there, the smaller waves, almost exactly match up, which is why when we look at the superposition of the two, the black curve, that it is basically twice the height of the two individual waves. Now, let's go a little bit later in time. I'm going to go up to half a second later. And we'll see that because the frequencies are slightly different, when I run that, we see eventually the red and the blue waves get out of phase. So that when the red is at a peak, the blue is at a valley. So they almost exactly cancel out, but it doesn't last very long. Very quickly, the two waves start to come back into phase. And you can see the black curve starts to grow again. Now, let's say I were to look at this over a longer time scale. So let me just change my scale to go from 0 to 5. Actually, this will be easier if I take out the red and blue curves. We can see my waves, when they start off in phase, I get a nice big amplitude, but that amplitude shrinks over time. Now, if I look at an even longer period of time, you can see we start to get beats here. Beats arise naturally because of the way the sine waves combine. So when the frequencies are slightly different, they're going to go in and out of phase periodically because they almost match up, but not quite. So if you wait a little while, they'll come out of phase, we'll lose the amplitude. If you wait a little while longer, they'll go back in phase and you'll get amplitude back. Mathematically, we can predict what's going on by looking at the sums and difference formulas for sine and cosine waves. Because by simply combining sine and cosine waves, we can come up with a formula that predicts the shape of this beat function.